Hello everyone, welcome back to SciFun Academy, where science is made fun. This is the first part of Chapter 3, Atoms and Molecules. In today's video, we'll be looking at the laws of chemical combination. Imagine a time over 2000 years ago, long before microscopes, test tubes or labs, when philosophers sat under the stars and asked one big question: what is everything around us made of? In ancient India, a wise man named Maharishi Kanad had an idea. He thought, what if we kept breaking a piece of matter into smaller and smaller bits? Eventually, we'd reach something so small that it couldn't be divided any further. He called this tiniest piece of matter Parmanu. Meanwhile, on the other side of the world, Greek thinkers like Democritus were having a similar aha moment. They called their smallest particles atom, which means indivisible in Greek. But here's the catch. This was all just guesswork. No experiments, no proof, just big brain energy. Fast forward to the 18th century, the age of experiments. Scientists like Antoine Lavoisier and Joseph Proust decided to test these ancient ideas with real chemistry. And guess what? They discovered some major laws that still shape how we understand matter today. First up, Lavoisier's big discovery, the law of conservation of mass. It says that mass can neither be created nor destroyed in a chemical reaction. In other words, the stuff that you start with always equals the stuff you end up with. No more, no less. Okay, take a solution of copper sulfate in a test tube and sodium carbonate in a flask. Seal the flask. Carefully mix them and you'll notice a new substance forming, a beautiful insoluble precipitate of copper carbonate. But here's the kicker. When you weigh the flask before and after the reaction, the mass stays exactly the same. That's because no matter what new substances form, the total mass of reactants and products is conserved. Imagine making lemonade, for example. You mix water, sugar, and lemon juice in a glass. After stirring, even though everything looks different as it dissolves, the total weight of the lemonade equals the weight of the water, sugar, and lemon juice you started with. What do you think about a pencil? It gets smaller and smaller over time. Isn't the pencil disappearing? Well, no. Let's do an experiment. Here are some items you're going to need for the experiment. A pencil, a sharpener, a small container or bag to collect the shavings and lead dust, and finally a scale to measure the pencil's mass before and after sharpening. We start by weighing the pencil. Next, we weigh the empty container. Now, sharpen the pencil, collecting all the shavings and grated lead dust in the container or bag. Weigh the pencil again. You'll notice that it is shorter and lighter. Weigh the container with all the collected shavings and lead dust. Subtracting the mass of the container will give us the actual mass of just the shavings. Now, when you add the mass of the shavings to the mass of the remaining pencil, you should find that the total mass is the same as the original mass of the pencil. Pretty cool, right? Now let's talk about Joseph Proust and his law of constant proportions. He discovered that no matter where you get your water, from a glacier, a pond, or even your kitchen tap, it's always made up of hydrogen and oxygen in the same mass ratio of 1:8. 1:8? What? I thought water had a 2:1 ratio of hydrogen to oxygen. So where's all this 1:8 business coming from? Okay, let's break it down. First off, yes, you're right. Water has 2 hydrogen atoms for every 1 oxygen atom. That's the 2:1 ratio we know of, but that is by atoms. But we are not talking about atoms here. We are talking about mass, and mass can be a bit different. Now, hydrogen is super light. If we could weigh just 1 hydrogen atom, it would be like really tiny. Let's call the mass of 1 hydrogen atom 1 floof. I know, sure, there's a technical term for atomic mass, but that's a topic for another video. Now, on the other hand, oxygen is much heavier. It's about 16 times heavier than hydrogen. So 1 atom of oxygen would weigh 16 floofs. And when we look at a water molecule, it weighs 2 floofs from 2 hydrogen atoms and 16 floofs from 1 oxygen atom. That gives us the 2:16 ratio, which simplifies to 1:8. And this ratio stays the same no matter how much water you have. 9 grams of water will always have 1 gram hydrogen and 8 grams of oxygen, whereas 900 grams of water will have 100 grams of hydrogen and 800 grams of oxygen. And just like water, this concept applies to other molecules too. Take ammonia, for example. It has 1 nitrogen atom and 3 hydrogen atoms. The nitrogen atom weighs 14 floofs, and each hydrogen atom weighs 1 floof each. So the ratio here is 14:3, which means 17 grams of ammonia will always have 14 grams of nitrogen and 3 grams of hydrogen. So thanks to Lavoisier and Proust, we now know 2 super important things about matter. Its mass stays constant, and its elements always combine in fixed proportions. These discoveries paved the way for modern chemistry. Okay, quiz time. First question. In a reaction, 5.3 grams of sodium carbonate reacted with 6 grams of acetic acid. The products were 2.2 grams of carbon dioxide, 0.9 grams of water, and 8.2 grams of sodium acetate. Show that these observations are in agreement with the law of conservation of mass. To show that the observations align with the law of conservation of mass, we need to verify that the total mass of the reactants equals the total mass of the products. Let's start with the reactants. 5.3 grams of sodium carbonate and 6 grams of acetic acid. Total mass of reactants is equal to 11.3 grams. Moving to the products, we have 2.2 grams of carbon dioxide, 0.9 grams of water, and 8.2 grams of sodium acetate. Total mass of products is 11.3 grams. Therefore, total mass of reactants is equal to total mass of products. Proved. Question 2. Hydrogen and oxygen combine in the ratio of 1:8 to form water. What mass of oxygen gas would be required to react completely with 3 grams of hydrogen gas? Okay, 1 gram of hydrogen requires 8 grams of oxygen to form water. So 3 grams of hydrogen requires 8 times 3 or 24 grams of oxygen to form water. Question 3. A 0.24 gram sample of compound of oxygen and boron was found by analysis to contain 0.096 grams of boron and 0.144 grams of oxygen. Calculate the percentage composition of the compound by weight. Okay, the formula to calculate the percentage composition of the compound by weight is as follows. Percentage of the element is calculated by the mass of the element divided by the total mass of the compound times 100. Here's what's given. Total mass of the compound is 0.24 grams. Mass of boron is 0.096 grams. And mass of oxygen is 0.144 grams. So to calculate the percentage of boron, we have 0.096 divided by 0.24 times 100. This gives us 40%. And to calculate the percentage of oxygen, we have 0.144 divided by 0.24 times 100. This gives us 60%. Okay, final question. 3 grams of carbon reacts with 8 grams of oxygen to produce 11 grams of carbon dioxide. So 3 grams of carbon reacts with 50 grams of oxygen to produce how many grams of carbon dioxide? Which law of chemical combination will govern your answer? Okay, the law that we are looking at is the law of constant proportions. Carbon and oxygen always combine in a fixed ratio to form carbon dioxide. So 3 grams of carbon reacts with 50 grams of oxygen to still produce the same 11 grams of carbon dioxide. This is because of the fixed ratio. The excess 42 grams of oxygen will remain unreacted. Great job, guys. Now let's look at some key takeaways. Law of conservation of mass. Mass is neither created nor destroyed in a chemical reaction. The total mass of the reactants equals the total mass of the products. And law of constant proportions. In a chemical compound, the elements are always combined in the same mass ratio. For example, water is always made of 1 part hydrogen and 8 parts oxygen by mass. In our next video, we'll be discussing Dalton's atomic theory. And that's it for today, folks. Thanks for watching. If you learned something new today or just feel smarter than you were 5 minutes ago, hit those like, share, and subscribe buttons and stay tuned for more mind-blowing science. See you in the next one.